afternoon and welcome to the 2021 Transportation Infrastructure Durability Conference. My name is Wayne Frankhauser and I'm the Bridge Program Manager with the Maine Department of Transportation. And today I am going to present on composite use in Maine infrastructure and a brief outline of my presentation. I'm going to talk briefly about the needs for more durable bridges in the state, some of the FRP solutions that we've employed, and some of the next steps that the bridge program at DOT is looking to take. So for starters, why do we need more durable bridges? Well, I think it's no secret that our bridges live in a very harsh environment. They are constantly exposed to salts, whether it be salt water or de-icing chemicals. They suffer a lot of wear and tear, a lot of freeze-thaw cycles. And because of this, they're very expensive to maintain and very expensive to replace. This bridge that is shown in the photos to the right is a typical interstate overpass structure. And you see, these similar corrosion issues repeating over and over again on like bridges. Steel rusts, concrete deteriorates as the chlorides reach the reinforcing steel and it starts to expand. The wearing surfaces rot and allow chemicals to attack the top of the deck. We like many other states, have a significant unmet need each year, and it's difficult for us to maintain and replace these bridges as they come due, and if they don't necessarily last as long as we'd like them to last. So what do we do? How do we deal with this situation? At Maine DOT, we focus heavily on preserving what we have. If we can make our bridges last longer, it's much more economical than a replacement. But sometimes that's just not necessary. Sometimes the cost and the work associated with preserving or keeping an existing bridge in the inventory really outweighs the cost and the impact of replacing. So when we do replace a bridge, we want it to last as absolutely as long as we possibly can. So we build it to last, an extended service life of in the neighborhood of 100 years. And we typically do that by, looking back at the inventory of bridges we have and seeing what did work and what didn't work. We're very careful on the type of bridges we select. We like to think that we use better detailing and construction practices. And primarily, we use corrosion-resistant reinforcing steel, corrosion-resistant building materials. And a lot of that happens to be composites, such as composite reinforcing, composite drains, composite girders, etc. So next, just to highlight a few of the FRP or the composite solutions that we've come up with. And these first few are, I'm labeling, I guess, for lack of a better term, are FRP bridge systems. And they include, the composite arch bridges that are shown in the photo, HC beams and FRP tub girders. These tend to be the more substantial full bridge style composite replacements. The composite tub girder, formerly known as the bridge in a backpack, and what is known now as a G arch, was originally developed by University of Maine. And now it's licensed to AIT, but it consists of composite tubes that are filled with concrete. It has an FRP decking system, and then it has more of a conventional head wall system and a foundation system, and it's filled with gravel and has a bituminous wearing surface on top. So easy to construct, very durable, just due to the nature of the corrosion resistance of composites. These are going to be long lasting, easy to construct structures. We currently have 8 of these bridges in the inventory in Maine. Next solution that we've used are the HC beams. These were developed by John Hillman and tested at the University of Maine. This photo shows Booth Bay Barters Island Bridge, which was completed in 2012. It's 8 spans at 540 feet long. And the HC beams essentially consist of a FRP shell that encapsulates a concrete and steel tied arch. So it's truly an example of a kind of marrying of conventional and composite bridge materials. But again, inherently corrosion resistant due to the nature of the composites, lightweight, easy to construct. And we hope that it'll be around for years and years to come. Maine currently has 4 of these type of superstructures in the inventory right now. So the next couple photos again shows the Barters Island, just to kind of demonstrate the difference between what was there. To the left is a photo of the existing bridge that was replaced with the hybrid composite superstructure to the right. But the existing bridge had steel over salt water. It had many timber pile bent piers. It was a constant source of maintenance and cost for repairs, whereas the replacement bridge will hopefully require extremely minimal maintenance and will last considerably longer than the previous one did. Next up, I want to briefly talk about, and I know there'll be a couple other folks talking about this new beam system, but the FRP Tub girder systems. This was also developed by the University of Maine in conjunction with AIT Bridge. This is one of the newest girder technologies. Again, it's an FRP Tub girder. This bridge that's shown of the cross section of was the Hamden Gristmill Bridge, which was actually open to traffic late last year. They closed it again this year and reopened it after the contractor finished some minor work. But this project has been the focus of quite a bit of attention. And again, we at Maine DOT think this is a very promising solution. Again, it's corrosion resistant. It was extremely lightweight. Let me jump to the next set of photos. These show the bridge actually under construction to the right, and the G beam sitting in the AIT Bridges facility after fabrication. You can see the shear studs on top, so it's a beam that acts compositely with the concrete deck, allowing you to increase the spans. The photo to the right of the beams in place on the abutments, the contractor was very pleased. It had utilities that ran under the bridge, and the contractor was able to connect 2 of the beams and the utilities and swing those in place with a normal size crane that they would have on the site. So they were very pleased with the ease of construction and the lightweight nature of these FRP tub girders. So all around a very successful project. And the next slide shows another bridge in Hamden, the Twin Bridge, that's under construction currently, that's going to be using the next generation of G beams. And they consist of shallower beams that have a 4-inch concrete stay-in-place form cast on the top, so it turns it into a 2-beam system that can be brought to the site and easily and rapidly set in place to build a bridge. Again, this is just starting construction now. I believe the first of the girders is under being manufactured as we speak. Next, I want to jump into FRP solutions. Not necessarily the bridge systems, but the components. Obviously, one of the major sources of frustration for us is deterioration of concrete caused by chlorides reaching reinforcing steel, conventional steel reinforcing and expanding it. So therefore, we've switched pretty significantly to corrosion-resistant reinforcing, a lot of which is glass fiber reinforcing bars. We've used quite a lot of it over the past 3 years. Our objective here is to really get our bridge decks to last the life of a bridge. Right now, they do well. The typical interstate bridge, a lot of those are 60, a little over 60 years old. We're starting to replace complete bridges and replace some of the decks. But if we could get a bridge deck to last the length, the life of a bridge, say, 80 to 100 years, that would save us a tremendous amount of effort and impact to the public when it comes time to replace the deck. The next I wanted to briefly mention is, it's really obvious, but I think it demonstrates kind of the flexibility of FRP composites. But bridge drains, they see the worst of the worst as far as salt water and runoff from the deck. And they steel drains that you can see to the left rust out very fast, and then they kind of drool or spill that contaminated, that chloride laden water onto the rest of the steel structure, and it causes, or concrete causes, pretty accelerated deterioration. So FRP, we've switched primarily to FRP bridge drains, just because they don't rust out. Next is another application that I think really kind of shows the versatility of FRP composites, but this is a wrap, an FRP wrap that can be done in the dry or underwater. We have a lot of these old steel pipe pile bent pier bridges in the state. They're very economical to build, very easy for the contractor to construct. So we built quite a few of them. Unfortunately, the coating on the steel pipe is prone to abrasion or prone to nicking during construction. And then you start to see, the loss of the coating and the loss of the structural steel, well before we start to lose significant section and structural capacity. We like to come in and do these, something like this FRP wrap, and this has been done in a few cases and has been very promising. So a few other applications. The photo to the right is a carbon fiber pre-stressing strand that was used to make precast concrete next beams out of. So again, using the composites in concrete to address an issue, a potential corrosion issue like the corrosion of the conventional steel pre-stressing strand. But some other applications include concrete repair using FRP, FRP culvert invert linings, fender systems, wind fairings, again the CFCC pre-stressing and post-tensioning, and even carbon strand in our cable stay bridge. So the next steps, as we see them at Maine DOT, I think as you saw from the previous slide, there's a lot of applications that are coming out, and we definitely plan to stay alert and stay tuned to see what the latest, what the new solution is. What's the new composite solution that's out there that can help us. We're looking at standardization of just about everything. A lot of the uses we've used the composites on have been demonstration style projects. And we are looking to standardize. We're looking to develop our standards, standards and specifications and manuals to include composite materials. We need to explore contracting methods. One of the difficulties with composites is that they are, especially the composite bridge systems, is that they're proprietary. And although we can work around that, it's not how we typically do things. We typically put out contracts that have materials that the contractor has, multiple options to source. So we're looking at what's the best way to put it out to contract. Is it bid options? Is it are we going to specifically call out a proprietary composite beam? That's something that we need to explore before we can really kind of mainstream these solutions, and always training and education, the training and education across from design to fabrication, um, right out through the inspection of the in-service bridges that use composite components or systems is really critical next step for us to tackle. So um, that is it for me. I've run a little bit long. So with that, I will say thank you all for attending, and